Western Institute for Advanced Study was founded with the ambitious goal of solving intractable problems in science. The first grand challenge, issued in 2018, was to provide a physical explanation for consciousness. Dr. Izi Stoll is here to report her method of solving this problem by explaining consciousness in terms of probabilistic computation in cortical neural networks.
Today I'll be talking about consciousness as an emergent property of probabilistic computation in cortical neural networks. And I would think this theoretical framework will come as no surprise to neuroscientists, even though we haven't until now really been able to articulate a full mechanistic explanation that accounts for some of the more intangible features of cortical information processing. So consciousness is an ill-defined problem. There's not really a strict definition that everyone agrees on. But I would argue that consciousness is an ability to perceive the world, build an understanding of the world, and navigate the world through behavior. To break it down further, we can say that consciousness involves a number of steps which are inherent to the process of computation in cortical neural networks. First, consciousness involves perception. We experience a cohesive stream of information content, which corresponds to data acquired by the sensory apparatus. This perceptual experience corresponds to incoming data from all available sensory modalities, and perceived stimuli generally correspond to both objects in the local environment and the cortical coding of these stimuli. We know a lot about the cortical processes underlying perception, from feature extraction in visual cortex and auditory cortex to the what and where information that's encoded in the ventral and dorsal stream pathways, respectively. But we don't really know why this cohesive stream of perceptual experience occurs. Why is there this representational aspect to it? Consciousness is also about memory formation and memory storage. We're aware of past events, and we can access this information to navigate similar contexts. Memory formation corresponds to the remodeling of synaptic connections between cortical neurons, and memory recall corresponds to the activation of these same pathways. We know that structural plasticity is required for learning new skills, and we know that the structural integrity of synapses is lost during age-related cognitive decline, particularly in cases of dementia where memory is disrupted. Consciousness is also about cognition. We build an understanding of the structure and operation of the world, in both general terms and under specific circumstances. We also build skills to navigate that world through language and behavior, and we grow to understand our own capabilities and constraints as we do so. Cognition corresponds to the accumulation of knowledge over time, as we observe the world and make logical inferences about it. And we develop these cognitive models of the world and ourselves through feedback over the course of multiple sensory motor loops. We essentially try out hypotheses and evaluate how well these hypotheses hold up when they're tested in reality. And so consciousness is also about prediction. Incoming sensory data does not always agree with existing cognitive models. If new information is presented, we have to decide if that incoming sensory data is wrong, or if our own cognitive models that have been built over a lifetime are wrong. Predictive processing in cortical neural networks corresponds to error signals which prompt orientation toward a stimulus so that further information can be gathered. We may not find it sensible to discard a well-established cognitive model in favor of new information. But if this new information provides important survival value, then it is wise to update our cognitive models to accommodate the new information. And I think we've all really seen this play out over the past year or so as everyone decides whether to believe in COVID or not, for example. And finally, consciousness involves behavioral choice. We are not purely deterministic entities with entirely predictable output behavior. Our actions are not automatic like spinal reflexes. but rather they are the result of decision-making in cortical neural networks. Descending motor signals are prompted by the integration of newly arriving sensory data, contextually relevant memories, and a general understanding of how the world works, as well as the predicted effects of each possible action. We take into account a combination of information to make a conscious decision, and then we select behavior to meet our goals. Classically, when we think about the nervous system as neuroscientists, we think of sensory input and motor output, with neural coding occurring in between. And that works really well for simple neural circuitry like spinal reflex circuits, where neural coding is really the sum of all upstream inputs. But it doesn't really work for cortical neural circuitry, which is a lot more complex. Specifically, we haven't been able to explain some of the emergent properties of cortical coding, which are not characteristic of spinal reflex circuits. These properties include streaming perceptual experience, cognitive models, which are characterized by memory storage and predictive processing, and the voluntary initiation of behavior. We know that cortical activity is required for each of these phenomena, but we haven't been able to explain how cortical neural activity bridges to these intangible features. That has been a real challenge. And so there must be something unique about cortical neural networks which give rise to streaming perceptual experience and cognition and voluntary initiation of behavior. So what's unique about cortical neural networks? First, they're noisy. Random electrical noise prompts membrane potential fluctuations in cortical neurons and actually affects cortical neuron signaling outcomes. That is not true in spinal reflex circuits or peripheral sensory neurons. These cells have deterministic outcomes, which are robust to noise. Next, cortical neurons are extraordinarily energy efficient, while spinal neurons are only about 50% energy efficient. Multiple studies have found that cortical neurons seem to be over 90% energy efficient. And this is really understudied, and I think the reason is because this finding is so bizarre. Next, cortical neurons have accurate but unpredictable signaling outcomes. Cortical coding is best modeled with probability distributions of spike counts or signaling outcomes from random projections. Again, this is not true with spinal circuitry or peripheral sensory neurons. These cells have deterministic outcomes, which are easily predicted by either summing upstream inputs or identifying a suprathreshold stimulus in the receptive field. Next, cortical neurons exhibit synchronous firing across sparsely distributed neuronal populations. Cells across a cortical neural network will periodically fire simultaneously. And a number of mechanisms underlying this temporal binding have been studied, but really a full mechanistic explanation for a system-wide coordinated recruitment is still uncertain. And again, it should be noted that spinal circuits and peripheral neurons do not exhibit this kind of behavior. And finally, cortical neurons spontaneously undergo structural remodeling to encode memory. And really, it's these temporally bound coordinated firing patterns that prompt spontaneous structural remodeling. And again, this is not something that happens in spinal circuitry. So these are the unique characteristics of cortical neural networks. Let's go through each of these characteristics again. Random noise increases the amount of entropy produced by a thermodynamic system, which normally wastes energy and reduces accuracy in electrical circuits. And yet, cortical neural networks are incredibly energy efficient, doing far more work for the amount of energy expended than any other tissue or any other engineered system. But despite permitting random electrical noise to influence signaling outcomes, cortical neurons accurately represent very specific stimuli in the local environment. And this accurate and specific coding by individual cortical neurons occurs simultaneously across sparsely distributed cell populations, with cortical neural networks exhibiting periodic firing at a range of frequencies. And again, while a number of mechanisms have been found to explain this temporal binding of signaling outcomes, it's been very difficult to explain how network-wide recruitment could spread with highly coordinated temporal dynamics without leading to epileptic activity. And finally, the emergence of a more ordered system state during development and learning locally violates the second law of thermodynamics. Again, I'm not arguing against the molecular mechanisms of long-term potentiation, long-term depression, and other modes of synaptic plasticity. These are well-established mechanisms for achieving structural remodeling in cortical neural networks. But these mechanisms do not address how entropy can be physically reduced over time in a non-equilibrium thermodynamic system. That requires explanation on its own terms. So let's go over this list one more time. We have noise, which means we have maximal entropy production during cortical neuron computation. And we have extraordinary energy efficiency, which means we have minimal net entropy production during cortical neuron computation. So these two things do not agree. We're creating a lot of entropy during probabilistic coding, but then it seems we're not producing much entropy, and instead we're remaining highly energy efficient. Next, we have accurate but unpredictable signaling outcomes. So this is an unlikely outcome, but one that encodes information. Then we have synchronous firing across sparsely distributed neuronal populations. Again, this is an unlikely outcome, but one that encodes information. And also, we have spontaneous remodeling of the neural network structure to encode memory, which is, again, an unlikely outcome, but one that encodes information. So what do we have here? We have a lot of information, a lot of unlikely events, a lot of entropy forming. But at the same time, we have enormous energy efficiency with little net entropy production. So what we have here is a very interesting thermodynamic system, which is capable of finding itself an optimal system state through noisy information processing. So what I'd like to do is explore how this special kind of non-equilibrium thermodynamic system works. That is, how energy is distributed to generate and compress information in order to select an optimal system state in the context of a massive probability density. So the hypothesis here is that tracking how energy is expended toward entropy, which is an expansion of the number of possible system states, will help to explain how cortical neural networks encode useful information by identifying the most optimal system state. The aim here is to explain how a system-wide, non-deterministic computation is achieved with extraordinary energy efficiency and local memory storage. So we end up with an optimal system state, an increasingly ordered system state, and a permitted violation of the second law of thermodynamics. So the question here is really, do neurons encode information or do they encode entropy? To move forward here, I think it's worth recognizing the relationship between these two quantities. So Shannon information, which is used in classical computing, is the sum of all possible system states multiplied by the natural log of that number. Meanwhile, Gibbs entropy, which is used in classical thermodynamics, is also the sum of all possible system states multiplied by the natural log of that number, but now also multiplied by the Boltzmann constant. And von Neumann entropy, which is used in quantum mechanics, is the sum of all possible system states in a matrix of any dimensionality. This last equation really links thermodynamics and information to probabilistic events that are occurring at the particle level or the ion level. And what I'll argue is that von Neumann entropy is really the most appropriate way to model the type of information entropy being produced by neurons because they're harnessing stochastic charge flux to get a state change in the macro-scale computational unit. So now we're ready for a new approach. Here, I'll just outline the rest of the talk so you know what's coming. First, we'll compare the current approach in neuroscience, which asserts that neurons are best modeled as classical computing units, always in an on state or an off state. And we'll contrast that with a new approach, which asserts that cortical neurons are best modeled as qubits, suspended at the threshold of firing and action potential, and sensitive to quantum level noise in gating a state change. Next, we'll go over a mathematical model of non-deterministic computation in terms of thermodynamics, where energy is distributed toward information generation and recovered upon information compression. Then, we'll go over a mathematical model of non-deterministic computation in terms of mechanics, where any energy above ground state populates a Hamiltonian, and that energy is redistributed as the Hamiltonian is solved. Next, we'll go over a mathematical model of non-deterministic computation in terms of complex waves. These wave functions, or probability densities, impinge on the neural membrane surface to both encode and represent physical information. Constructive and destructive interference then resolves the probability density into a single non-deterministic outcome for every computational unit in the system. And the upshot of all this is that all three mathematical models naturally yield a cycle of energy expenditure and recovery, corresponding to a cycle of information generation and compression. And so finally, we'll go over the assumptions of this theoretical framework, as well as its explanatory power and some specific predictions which can be tested in the laboratory. Okay, so let's compare the classical model of the neuron with the new approach. First, let's look at how we currently model the neuron as a classical computing unit, with each neuron in the network acting like a transistor, always in an on state or an off state. Here, each neuron has some microstate pi equal to 1 or 0. If the spike in behavior of every neuron is random, the probability of any single microstate pi would be 1/2. And the number of possible macrostates, Pa, is 2 to the n. The amount of information entropy is the sum total of macrostates Pa in a system with n neurons, each with some microstate Pi that is equal to 1 or 0. And so the probability of any one macrostate Pa represents all possible combinations of microstates Pi for the set of neurons n, each of which is in an on state or an off state. This is the Shannon entropy of the system, or the amount of classical information held by the system. Since there are 80 billion neurons in the human cortex, there are a lot of possible combinations, and any one outcome is highly unlikely. Basically, the larger the number of neurons, the lower the probability of any given macrostate, and the greater the amount of information held by the system. But any active neural network with n greater than 0 has some amount of information, which is given by h. This model assumes that all cortical neurons are either in on state or off state at any given time. But this model ignores the fact that cortical neurons spend most of their time in up state, hovering right near the threshold for firing an action potential. So let's look at another way to model that behavior. Here, we're focused on the state of the neuron as it's integrating multiple noisy upstream inputs to determine its present voltage state. Neurotransmitter-gated ion channel opening leads to ion flux, but there's some leak across the membrane as well. The state of each ion, inside or outside a given neuron, is dependent on the resistance of the membrane. And there are also spontaneous stochastic events which contribute to whether the neuron has reached voltage threshold or not. And so upstream signals converge and ions stochastically interact with the cellular membrane, and the voltage state of a cortical neuron changes over time. So we're not describing cortical neurons as binary computing units here. We're describing cortical neurons as qubits, which are superpositioned between an on state and an off state, integrating upstream signals and noise. The neuron starts out in off state phi, not firing an action potential. And over time t, it moves to another state, chi. Over this period of time, from t0 to t, the state of the neuron evolves from phi to chi. And so we always read this bracket notation from right to left. The time path taken from the initial state is therefore the expectation value for the state change through a linear operation given by the U matrix. The sum of probability amplitudes underpinning a state change can be represented in some basis, with U completely described by a matrix with orthonormal base states I and j. So here we have the complete basis for transitioning from phi to chi through the orthonormal base states I and j and the unitary operator, which we'll get to more in a moment. The state of the neuron is given by the orthonormal base states I and j, each with some probability amplitude ci and cj after some time has passed. So we're looking at the probability amplitudes after delta t. And the sum of the squares of these complex valued probability amplitudes is always 1. Okay, so the neuronal state at time t can be described as a normed state vector psi with a superposition of two orthonormal base states with probability amplitudes ci and cj. Since a neuron starts the time evolution in state j, its probable state at time t is given by the probability of converting to another state. And this is described by the sum of all probability amplitudes across all linear operations. If delta t equals 0, there's no state change and I equals j. If delta t is greater than 0, there is some probability of a state change where I does not equal j. And so the two-state quantum system is described by the Kronecker delta, which provides two orthonormal base states, with the cell switching to an on state if I does not equal j, and the cell staying in an off state if I does equal j at the end of that time evolution. Here, each neuron is considered a two-state quantum system with some probability of undergoing a state change. The neuron starts the time evolution below the threshold for firing an action potential, and it has some probability of reaching that threshold over time. And so the state of any given neuron at time t is a state vector psi with a superposition of two orthonormal base states, psi on and psi off. The probability of any outcome, if there's no knowledge of the previous state, is given by a density matrix ρ, which is the sum of mutually orthogonal pure states ρx, each occurring with some probability px, where the statistical ensemble of microstates is described by ρx, with ρx defined as an outer product which creates a finite dimensional vector space through matrix multiplication. And here, the probable state of the system is given by the quantity of von Neumann entropy, which is the trace across the density matrix ρ, where ρ is a mixed state given by the sum of all component pure states are the sum of all vector spaces. And it's worth remembering that the trace is the slope of that probability density. So if it's high, there are relatively certain outcomes and not much entropy. And if that slope is low, then there's a broad probability density and a lot of uncertainty and a lot of entropy. Okay, So we're just doing vector algebra with this fancy bracket notation. And so to summarize the model here, we're just describing how neurons reach a signaling outcome or an optimal system state in context. And this is really just a more sophisticated method of describing the leaky integrate and fire model. So in this new approach, each cortical neuron is a two-state quantum system with some probability of firing. And the entire neural network is a mixed sum of component pure states. And the information held by the neural network, or the sum of all possible system states, is described by a density matrix. And so now we can go over some rules for physical information processing. Rule 1 is the rule for distinguishable states. Redundant physical states cannot coexist. This redundancy is naturally reduced or compressed. And for this reason, the quantity of Shannon entropy will always be greater than the quantity of von Neumann entropy in a system that is able to physically generate and compress information. That leads to extraordinary efficiency in encoding information. Rule number 2 is the first law of thermodynamics. Energy cannot be created or destroyed. And so any energy that is expended to produce entropy must continue to physically exist. And the quantity of energy lost to the system is exactly equivalent to the amount of entropy produced. Rule number 3 is the Landauer principle. It states that free energy is recovered upon information compression, and the amount of free energy recovered is exactly equivalent to the amount of information compression. And this has been empirically demonstrated time and again over the years. All right, so now we're ready to go over a mathematical model of non-deterministic computation in terms of thermodynamics. What we want to do is describe the changes occurring in a density matrix over time. To do so, we have to think about how the system changes over time by interacting with its surrounding environment. Here, system A is the cortical neural network given by row A. It's a non-dissipative and far from equilibrium system perturbed by its surrounding environment. It has incoming caloric energy from the bloodstream and incoming electrochemical signals from the sensory apparatus. And these inputs are trapped in the brain. It acts as a net heat sink. System B is the surrounding environment given by row B, which perturbs system A. And we want to model the combined system created by the tensor product of these two density matrices. And in doing so, we find the tensor product of the two Hilbert spaces, the vector space of the combined system. And what we want to do is identify how that combined system evolves over time, as system A is being perturbed by system B. And what we'll find is that without significant energy dissipation to the surrounding environment, system A acts as a heat sink and uses the energy acquired from system B to drive computational work. And that work will happen over time t. The two system states are additive, and the entropy remains unchanged by the time evolution itself. But any states that are correlated or non-distinguishable will lead to entropy compression, and that's because entropy is additive in not uncorrelated systems, but subtractive in correlated systems. Mutual redundancies in system states are naturally reduced because they simply can't coexist. So now we'll look at the U matrix and the unitary change of basis to find out how exactly this compression occurs. As system A is perturbed by system B, the density matrix undergoes a unitary change of basis. The combined system evolves over some period of time through this linear operation given by the U matrix and its complex conjugate. The unitary change in basis is provided by the time shift operator U. And here we're introduced to the Hamiltonian operator H hat, which is the sum of all potential and kinetic energies in the system. U is represented by a square matrix of finite dimensionality. And since both time and energy are intrinsically uncertain, this U matrix represents all possible energy states emerging over time. And it's really only when these time and energy matrices commute that we can get a resolution of the system state. So the product of this U matrix and its complex conjugate is an identity whose determinant is always equal to 1. The columns of U form an orthonormal set of column matrices, and the rows form an orthonormal set of row matrices. If system A and system B become correlated during the unitary change in basis, the rows and columns of the matrix become linearly dependent vectors. That means these vectors are overlapping or redundant to each other. And that internal consistency allows compression of the combined matrix since the volume of that parallel pipette approaches 0. And so the identification of linearly dependent vectors during the unitary change in basis leads to dimensionality reduction because we found a 0 determinant for the density matrix. And that's really how the identification of correlations between system A and system B compresses quantum information in terms of matrix mechanics. The reduction in von Neumann entropy yields observables on the boundary region of the probability density as eigenstates are resolved. And that means redistributing energy to actualize the optimal system state out of all possible system states. So now we can find out how eigenvalues are realized. And we'll start with a square n by n matrix with an orthonormal basis. That is, all values in the matrix are linearly independent unit vectors. A vector V is an eigenvector within a square n by n matrix called A if it acts as a scalar, so that matrix A is stretched in a scalar manner by the eigenvalue lambda. And for each eigenvalue lambda applied to an n by n identity matrix, there's a correspondingly scaled matrix A. And conversely, you could say for each matrix A, there are some possible eigenvalues or scalars. And finding the 0 determinant for this eigenvalue equation yields all possible eigenvalues, given by the nth order characteristic polynomial p lambda. The nth order characteristic polynomial equation has n sub lambda distinct solutions, with n sub lambda between 1 and n. The spectrum of matrix A, or the set of eigenvalues for matrix A, is given by the number of factors for the characteristic polynomial p lambda, where all algebraic multiplicities summed to n sub lambda equal n. And it's important to note that not all eigenvalues are necessarily linearly independent, which means the geometric multiplicity may be smaller than the algebraic multiplicity. And it's going to be useful to really pay attention to the relationship between linear algebra and geometry here. That is the key to understanding how entropy can be reduced to identify an optimal system state or how eigenvalues can be identified. There may be any number of algebraic solutions, but any of these solutions, if any of these solutions are redundant between the two systems, they can't both take up space. They can't both coexist as entropy, and so that redundancy is naturally reduced. So now we can generalize the process of factorizing matrices. Before, we took a square, normal, n by n matrix with an orthonormal basis through eigendecomposition. Now we'll take an m by n matrix through the process so we can identify correlations between the two systems. So we'll start with an m by n matrix, and this matrix undergoes a rotation given by an m by m unitary matrix called U. Then it undergoes a stretch given by this m by n rectangular matrix called D, which has non-negative real numbers on the diagonal. Then the new m by n matrix undergoes a rotation given by this n by n unitary matrix, which is a conjugate transpose of V. And all of these transformations together yield chi. the diagonal entries given by mu are called the singular values, and the number of non-zero singular values is equal to the rank of the chi matrix. The columns of U and the columns of V are the left singular vectors and the right singular vectors of the chi matrix respectively, and together they make up the diagonals. So we can think of the original M by N matrix as system A, and the D matrix as an observation or measurement of system B, which stretches the density matrix or possible states of system A. And once this algebraic transformation has taken place over some time evolution, we've decomposed the matrix and identified the correlations between the two systems. The rank of the chi matrix after these transformations is the number of pure states or vector spaces shared in common between both systems. And this is a measure of entanglement. If the rank of the combined system is only 1, the two systems are separable. If the rank is more than 1, the systems are entangled. And if the rank is equal to the total number of pure states or vector spaces, then the two systems are maximally entangled. So let's keep in mind how linear transformations can lead to matrix decomposition and the identification of eigenvalues. A mixed quantum state, given by the density matrix ρ, may have two different realizations, each given by a different ensemble of pure states, ρ1 or ρ2. And here, chi j and chi k are eigenvalues within the set of eigenstates chi, normalized so that these values sum to 1. These two different realizations are achieved by two different purifications, vector state 1 or vector state 2. And here, the square root of the eigenvalue chi is the Schmidt coefficient. And this is identified by taking the partial trace of the outer product of two density matrices to describe all possible outcomes or all possible singular values. And so the two purifications here only differ by a unitary transformation acting on the combined system. And for this reason, there's a unitary matrix U that can convert one state to another. So different ensembles of pure states can be realized by making different measurements, which means just applying a slightly different D matrix. This method, called Schmidt decomposition, permits the quantification of entanglement between two thermodynamic systems. The systems are separable if and only if there's one Schmidt coefficient. And if there's more than one non-zero Schmidt coefficient, the state is entangled and represented redundantly by both systems. And if all Schmidt coefficients are non-zero, the systems are maximally entangled. So Schmidt decomposition allows us to quantify the entanglement of a bipartite system, which applies to a cortical neural network, which is a far from equilibrium system A being perturbed by its surrounding system B. So if we're wondering how a cortical neural network identifies an optimal system state in the context of reality, the density matrix undergoes a rotation, a stretch, and a rotation. And at the end of this process, it's found correlations with its surrounding system. So how do we stretch ourselves to observe reality? If we think about this process in terms of thermodynamics, we're expending energy to expand the number of possible system states, to improve our chances of perceiving reality accurately, of finding ourselves a well-correlated state with reality. And so in this view, perception is an active process of searching reality and encoding what you find there into your neural network. So perception is finding yourself on the same complex plane as reality and allowing your neural network to become correlated with it. And so perception is an agreement to observe the outside world and construct an internal representation that matches with external reality. And that takes work, thermodynamic work. But if you do that work, the reward is recovering that energy back when you find correlations and compress that information and reduce that entropy. And so if you never expend energy to observe reality, you'll never gain predictive value and you won't understand how the world works and you won't be able to navigate the world effectively. But sometimes people do the work to build a cognitive model, but it has no predictive value, or that predictive value is wrong. In that case, the person needs to deconstruct the existing cognitive model and build a new one to replace it. But that requires a lot of energy dissipation or the erasure of work. And so it's not really thermodynamically favored to do so. And we'll get to how this process of information coding is related to representational information content in a bit. But for now, let's find out how a partial trace identifies the state of the system. The physical state of each neuron in the network can be described as a distribution of pure states. And each pure state occupies a Hilbert space, with an ensemble given by each state vector and its probability of occurring. So the density matrix representing all mutually orthogonal pure states is defined as a mixed state, comprising all of these component state vectors. And remember, the density matrix for an ensemble of mutually orthogonal mixed states across system A is given by the set of pure states rho x, each occurring with probability px. And so we can substitute all of these values into the equation to model how the density matrix is decomposed. Okay, so now we'll get to the partial trace. Taking the partial trace of rho AB over B yields the mixed state of subsystem A. And taking the partial trace of rho AB over A yields the mixed state of subsystem B. Since the vectors of subsystem A occupy a Hilbert space of a corresponding dimensionality, and the vectors of subsystem B occupy a Hilbert space of corresponding dimensionality as well, and these are both orthonormal sets, then chi I from 1 to n sub s are the eigenvalues of both rho A and rho B. So these two density matrices have the same spectrum of eigenvalues, and these redundancies can be reduced. The reduction of entropy is proportional to the reduction in Hilbert space caused by entanglement. And because we're looking at a two-state quantum system, that reduction in dimensionality is 2 to the n times entropy. And this equation is the Schumacher compression for a mixed ensemble of orthonormal pure states. This process allows system B to be discarded, as correlated states are identified in system A by the partial trace. And it's worth remembering here that Hilbert spaces are vector spaces with an orthonormal basis formed by linear algebra. They have a finite number of orthogonal axes, which are generally complex, not real. And these spaces are populated by complex valued probability densities that are generated by linear transformations of vectors. And so, if there are redundancies between vector states, they just occupy the same Hilbert space. And so you don't need that additional geometrical space to accommodate all of the information stored by the system. And that's how you get this energetic efficiency, because you can store a lot more Shannon information for the amount of vector space if there are correlations in the state of the two systems. And so the amount of Shannon entropy held by a system is always greater than or equal to the amount of von Neumann entropy in a system. The physical process of compression means that more Shannon information can be stored in a smaller amount of vector space. And that process is really what's behind thermodynamic computation. And we can identify the maximum amount of information compression that's possible by identifying the Holovo bound. Block diagonalization of the matrix realizes the eigenvalues from this ensemble of mixed states. And as you can see, we're extracting the predicted correlations between the two systems by taking the partial trace of the combined matrix. So this value of H is the Holovo bound for the quantity of information in the system. As eigenvalues are realized for the ensemble of mutually orthogonal mixed states during a computational cycle, the physical quantity of entropy held by the system is compressed. And so qubits carry more classical information, but only the non-redundant states can be retrieved or accessed. And so the amount of Shannon entropy that's gained during a computational cycle is equivalent to the amount of von Neumann entropy we started with minus those redundant states, or the predicted correlations between the two systems. And the amount of von Neumann entropy we started with is always greater than the number of predicted correlations, or the predictive value that's extracted from that probability density. We can't have more predictive value extracted than the amount of entropy we started with. And so predictive value is a thermodynamic quantity. The remaining uncompressed information is the amount of energy dissipated by the system in a computational cycle, or the amount of work dissipated toward the creation of von Neumann entropy. And that is equivalent to the quantity represented in the Stoll dissipation theorem. The working memory of the system that is accumulated over the course of a computational cycle is provided on the left-hand side of the equation. And that value is equivalent to the total amount of entropy on the right-hand side of the equation. And the predictive value of that information, given on the left-hand side of the equation, is the amount of compression achieved by the recognition of correlated states between system A and system B, which is given on the right-hand side of the equation. So the Schumacher compression that occurs as those two systems interact is equivalent to the extraction of predictive value during the computational cycle. And that quantity H is equivalent to the amount of information held by the system after compression has occurred, and it's always greater than or equal to 0. So some energy is always dissipated toward the creation of entropy during a computational cycle, and not all of it is necessarily recovered. This energy is essentially dissipated as thermodynamic work to create entropy, and a single computational cycle will not generally resolve all uncertainty. And so the amount of information gained during a thermodynamic computing cycle is limited by the amount of energetic resources. A thermodynamic computing cycle must always be perfectly accounted. The amount of caloric energy coming in minus the amount of heat energy lost minus the amount of work done minus the amount of Gibbs free energy must always equal 0. And any incoming caloric energy that is not accounted by heat, work, or remaining free energy is dissipated toward entropy during a thermodynamic computing cycle. And that net entropy is given by the amount of work dissipated toward creating Shannon information. Given an equivalence between the Stoll dissipation theorem and the Schumacher compression equation, some quantity of predictive value can be extracted during a thermodynamic computing cycle. But again, that quantity is intrinsically limited by energetic resources and the amount of energy dissipated toward entropy production during a computational cycle. Now we'll find that free energy is released upon information compression. And to find out how, we can revisit the fundamental equation in neuroscience, the Nernst equation, which calculates a temperature-dependent shift in the membrane electrochemical potential. Here, Vt is equal to V0 plus RT over Zf times the natural log of Qr, where Vt is the electrochemical potential of the cell after some time has passed, V0 is the starting potential of the cell, R is the universal gas constant, T is the temperature of the system in degrees Kelvin, F is the Faraday constant, Z is the valence of the ion that is transferred during the reaction, and Qr is the reaction quotient, which gives the equilibrium potential of the reaction, which in this case is, of course, the likelihood of ions crossing the neural membrane. And since the change in voltage equals the change in potential energy over charge Q, and charge Q equals the valence of the ion Z times the elementary charge E, we can simplify the equation. And since the charges Z cancel out, and ER over F equals KB, the Boltzmann constant, the equation can be further simplified. And we're really looking at the sum of all reaction quotients for all ions m in the vicinity of a neuron. Each ion has some likelihood of passing across the neural membrane over time t, and that likelihood is dependent on the distance from each electrochemical potential and the exact behavior of other neurons nearby. So we're really looking at the sum of a bunch of probabilities here. And that's, of course, where the Nernst equation originally comes from, the quantity of Gibbs free energy in a system. And that's the equation we're looking at here. So the Nernst equation can be termed as the likelihood of potential energy converting to kinetic energy over some time period. And that free energy can be used to do work in the system. So the Nernst equation can be termed as the likelihood of potential energy converting to kinetic energy given by the Gibbs free energy. And when predictive value is extracted, uncertainty is reduced and entropy is compressed. And since a thermodynamic computing cycle must always be perfectly accounted, then any loss of uncertainty must equal a gain in free energy. And what that means in practice is that free energy is released to any neurons that have extracted predictive value or found a correlation with their environment in a manner proportional to the reduction of von Neumann entropy. So any reduction in von Neumann entropy equals a gain in free energy. And because that changes the equilibrium potential of the reaction, that free energy is predicted to prompt the movement of ions into neurons that are losing uncertainty, thereby resolving the state of the computational unit. So neurons are expected to fire all at the same time as the result of a system-wide computation, and this synchronous firing is expected to correlate with the realization of a percept, which is really well in line with our understanding of high-frequency gamma oscillations occurring in sparsely distributed cells across the cortical neural network during wakeful awareness. So extracting predictive value during a computational cycle is expected to yield a semantic statement about the environment. Some quantity of predictive value is extracted during any thermodynamic computing cycle. And here, time is the duration of the computational cycle, the time over which information accumulates and correlations can be found between system A and its surrounding environment, system B. And this process yields a predictive semantical truth statement about the environment, about the state of reality. And if the computation is accurate, the percept will be accurate as well. Now we can extract predictive value during a sequence of computational cycles to yield a syntactical prediction about the environment. So we remember that not all entropy is compressed during a single thermodynamic computing cycle. Some quantity of entropy remains, and that's because there's still uncertainty regarding that percept. There's still predictive value to be potentially extracted. That entropy, or set of possible system states, can be integrated over time with subsequent percepts paired with subsequent possible system states. So some quantity of predictive value can be extracted from the total amount of integrated information that is gained during a sequence of thermodynamic computing cycles. And time in this case is the duration of several computational cycles, corresponding to a series of percepts and a series of events that are happening in the local environment. So now we're predicting a syntactical truth statement about the environment. We're building a cognitive model of cause and effect. That is, we're making a prediction about the likely cause-effect relationship between events that are observed to follow each other in reality. And if the computation is accurate, the predictive model will be accurate as well. And these compression events are predicted to correspond with synchronous activity across the neural network, but now with a longer periodicity than single computational cycles. So that would correspond to slower rhythms observed in cortical neural networks. So now we can summarize how these computational cycles affect behavior at the organism level. exploration exposes an individual or an organism to uncertainty, thereby generating information. And parsing predictive value reduces uncertainty, thereby compressing information. And the exploitation of knowledge that was previously gained through exploration makes good use of that predictive value. So we operate on a rival energetic cost function, always selecting exploration or exploitation behavior. If existing knowledge is sufficient to navigate a situation, no uncertainty will be generated and no entropy will be produced. Relatively deterministic outcomes should occur and relatively stereotyped behaviors should result. However, if existing knowledge is not sufficient to navigate a situation, there will be uncertainty and entropy will be produced. So in this model, consciousness manifests to handle these unprecedented situations. It is a process of non-deterministic computation to handle unprecedented situations. So exploration behavior generates new information, and exploitation behavior makes use of existing information. So we can handle anything that comes our way in an energy-efficient manner. So, in summary of the thermodynamic model, we have a far from equilibrium thermodynamic system that's capable of both generating information and parsing it for predictive value. That allows us to move from a prior probability density to an optimal system state in the present context, and then evolve a new probabilistic state from there. We have a network of 80 billion computational units that is capable of storing more information than would be possible with 80 billion transistors. And that's because qubits store more information than classical computing units. And we have an enormously energy-efficient system that produces a lot of information or possible system states, but then compresses that information to release free energy. And that is a process of thermodynamic computation. And we have a system that allows the resolution of uncertainty to drive signaling outcomes across the network. And the synchronous neural activity in sparsely distributed cell populations encodes information. And finally, we have a system that uses the free energy that is released when uncertainty is reduced to remodel the connections between computational units. And that encodes the predictive value into the structure itself. So these patterns of neural activity are thermodynamically favored to reoccur in the future when a similar context presents itself. And all of these features, which naturally emerge from this model of thermodynamic computing, are observed in cortical neural networks. The parsing of predictive value, the incredible information storage, the enormous energy efficiency, the synchronous firing of neurons across the network, and the spontaneous self-remodeling of the structure to encode memory. So now we can get into the mechanics underlying the process of thermodynamic computing. And that involves a completely independent mathematical model of non-deterministic computation in terms of quantum mechanics. So we'll be looking at what's happening at the particle level to give rise to this system-wide non-deterministic behavior. So let's revisit our starting assumption that a cortical neuron undergoes probabilistic coding and therefore is best represented as a two-state quantum system. We know that the voltage state of a cortical neuron changes over time as upstream signals converge and ions stochastically interact with the cell membrane. A neuron starts in off-state phi, not firing in action potential, and evolves into another state chi over time t. And so the neuronal state at time t can be described as a state vector psi with a superposition of two orthonormal base states I and j. Since a neuron starts the time evolution in state j, its probable state at time t is given by the sum of all probability amplitudes for all possible paths. And here we can see that rotation and stretch and rotation of the density matrix as we read the bracket notation from right to left. And that's how we find our system state at time t. And so the two-state quantum system is described by the Kronecker delta, providing two orthonormal base states for the two-state quantum system. And if delta t equals 0, there can be no state change and I will equal j. But if delta t is greater than 0, there is some probability of a state change where I does not equal j. So now we can model this process of neuronal state change with quantum mechanics. For small changes in t, each of the coefficients of the U matrix differ from the Kronecker delta by some quantity that's proportional to delta t, given by k, where k is negative I over the reduced Planck constant multiplied by h hat, which is our time-dependent Hamiltonian operator describing the distribution of energy across the system as a function of time. And here, I represents the imaginary unit, not the ith base state as before. And of course, h slash is the reduced Planck constant, and the Hamiltonian operator h hat represents each of the time derivatives of each coefficient of the U matrix. And so we can substitute this equation for the U matrix into our equation for Ci and find that our probability amplitude Ci is equal to the sum of all these possible energy distributions, which change as a function of time. And since the sum of the Kronecker delta times the probability amplitude Cj is just the state vector, the equation simplifies. So the time derivative of this probability function yields a state vector, or every possible path taken. And so any state change is a sum of all perturbations to the system affecting how energy is distributed across the system. And if we multiply both sides of the equation by the imaginary unit and the reduced Planck constant, we find a very familiar equation. The system is effectively described by the time-dependent Schrödinger equation, with any state change that occurs related to a change in energy distribution given by that Hamiltonian operator. So now we can model the mechanisms underlying this non-deterministic computational process at the level of electrons. That is the quantum mechanics underlying a thermodynamic computing cycle. Because whenever we generate and compress entropy, we're generating and compressing a set of possible energy configurations across the system. And that means solving for the Hamiltonian operator. And it's worth remembering that in this model, we're looking at a fractal-like quantum system. The neuronal state evolves over time, with the signaling outcome at time t being a function of the sum of all local ion states. And the state of each ion in the system evolves with time, with some probabilistic location at time t defined in relation to every neuron, either inside the neuron or outside of it. And the ion state is essentially a function of the electrical fields generated by the membrane potentials of all nearby neurons, as well as the position, momentum, and energy state of every component electron. And the position, momentum, and energy state of every component electron in the system evolves with time due to quantum uncertainty. And so the uncertainty at each level contributes to the state vector at the higher level, because that state vector is given by the sum of all component pure states. So what we'll find is that quantum uncertainty is quite useful for non-deterministic computation, and it's expected to contribute to signaling outcomes in cortical neurons during cortical upstates. So rather than looking at the state of every neuron in the system, we can look at the state of every ion in the system, which is either inside a given neuron or outside of it. Or we could model the state of each ion as the sum of all component states by modeling all possible states of each electron, which of course contribute to the ion's behavior in the presence of a dynamic electrochemical potential. So if we want to get down to it, we have to consider the inherently probabilistic position, momentum, and energy state of every electron in the system. The neuronal state is essentially the mixed sum of these component pure states, because the trajectory of every electron is going to affect the electrochemical potential of every nearby neuron. And the fluctuating electrochemical potential of every membrane is going to exert electrostatic forces on every electron. So we'll model each electron in detail. Each electron has some set of possible positions given by probability amplitudes distributed across the x, y, and z axes. And the electron will also have some set of possible energy states or atomic orbitals distributed across another axis. And some time has passed, but that quantity is also uncertain and provided by a set of probability amplitudes distributed along the time axis, which means the probable positions are changing as a function of time, and energy states are also changing as a function of time due to quantum oscillations. So we have 5 orthogonal axes and probability amplitudes distributed along all of these complex planes. And we'll only get observables or eigenvalues for each electron if all of these density matrices commute. That is, if correlations are found between the system and its environment. And if the density matrices don't commute, the energy that was expended to produce entropy to populate the Hamiltonian operator will be lost to the time and energy axes and won't be recovered by the system. And to realize these coarse-grained, system-wide outcomes, we really need to model the fine-grained processes. And that means mathematically modeling these algebraic transformations of component pure states, describing position, energy, and time. And again, it's really important to consider the relationship between linear algebra and geometry here. When we build a matrix describing the mixed sum of component pure states, or we think of a wave function representing all of those possible states, we're modeling the distribution of complex-valued probability amplitudes. But we have to remember that we're actually building vector spaces. And just as complex numbers are orthogonal to the real number axis, complex-valued probability amplitudes are orthogonal to observable reality. So if we think about a given object in space, a point or distribution of points on the x, y, and z coordinate plane, that object exists at multiple points along the time axis as well. So it's changing over time. And at each point in time, there may be any number of possible energies associated with that location. And that means there's a probability distribution along yet another complex plane, one that's orthogonal to the x, y, and z and t axes. So when we're trying to determine the optimal and thermodynamically favored state of a system, we're dealing with complex valued probability amplitudes. And that means we aren't just considering the linear algebra of matrices, we're also considering the geometry of these probability distributions along complex axes. And we have to think of every particle as having not only some position along the x, y, and z axes, but also some position along the time axis and some position along the energy axis. And that's what we're trying to solve when we're trying to find the optimal state of a system. So now we're modeling every component electron of every ion as a mixed state quantum system, and the sum of all these density matrices will define the voltage state of each neuron in the cortical network. And again, the system under consideration is effectively described by the time-dependent Schrödinger equation, with any state change related to a change in energy distribution. And remember, h hat is the Hamiltonian operator, providing a vector map of all energies in the system, and psi is the eigenvector for the probable state of the quantum system after some time t has passed. And so this wave function describes the eigenstate of an electron as a function of time and the amount of energy available for redistribution. And the state of the entire system is essentially the sum of all these component states. If vector states across the system are dependent on each other, then the system has to be described as a whole, as a mixed sum of component states. And in that case, all energies above ground state are potentially available to be redistributed. So the entire system state is best described as the sum of all probabilities for all possible paths taken by every electron in the system since the system state was last defined. So the time-dependent state of each electron traveling in a wave-like fashion across multiple axes is given by a wave function equation that relates any changes in the electron's position r to its momentum and its energy. And the state of each electron will contribute to events at the ion level and the neuron level. So to model the quantum state of the electron, we have to model its quantum oscillations. And so we'll model the probability distribution of the position and momentum vectors Rx and Sx given by Gimmel, with a weight function given by Wx, which is always greater than 0. And this yields the inner product of a Sturm-Liouville equation, with a weight function Wx mathematically representing a quantum harmonic oscillator. So this little weight function embodies the quantum uncertainty of the electron state, and it naturally generates a Hilbert space. If this operation is symmetric or Hermitian, such that RLS equals RLS, then all polynomials will form complete sets in Hilbert space with real eigenvalues and orthonormal eigenstates, and that'll provide solutions to the second-order linear differential equation, which we recognized from before. And here, lambda is a constant and L is a Hermitian operator defined by the real functions of x, alpha, beta, and gamma. So we're going to find the nth order characteristic polynomial and all of our eigenvalues, but now we'll be modeling that process with a wave function equation rather than with matrix mechanics, but it's all the same thing. So now we can identify the density matrix for all component pure states. The probability of any one outcome for R and S respectively is given by the density matrix rho, comprised of mutually orthogonal pure states rho x, each having some probability of occurring px. And here, the volume of rho is proportional to the ensemble of orthonormal pure states rho x. And so the quantity of possible states for the system is calculated by tracing the volume across the density matrix. And of course, this quantity is the von Neumann entropy of the system. And now we can model the state of the electron over time. The evolution of the density matrix rho is given by this Liouville-von Neumann equation, with eigenstates provided by the Hamiltonian operator and its Hermitian conjugate. So we can substitute the operator and the conjugate into the time-evolved density matrix, and that yields a probability for each inner product of the Hamiltonian and each pure state. And the sum of these complex valued probability densities tells us how the density matrix is changing over time. So the time-dependent Schrödinger equation for an entire system of particles, which are at least partially dependent on each other, is given by the relationship between the Hamiltonian operator and the system-wide density matrix as a function of time. And that's because the total amount of energy available to the system is no more than the amount of energy stored in the system plus the amount of energy that has entered the system over time t. And it's really important to think about what's going on here. Since the probable state of each electron depends on the state of all other electrons, which are also probabilistic, the whole system has to be considered together as a mixed sum of pure states. And that combined wave function relates each of the state vectors to the passage of time t and the Hamiltonian operator h hat, which sums all potential and kinetic energies for all particles in the system. And so the spectrum of the Hamiltonian operator is the set of possible outcomes at the point when the total energy of the system is measured after some time t has passed. If time is defined, for example, by the detection of coincident charge flux across a barrier, all other matrices commute, and eigenvalues for position and momentum are observable. So let's find out how that happens. The Hamiltonian operator is related to the Lagrangian function of position r, its time derivative r dot, and time t. And it's calculated by taking the Legendre transform in order to minimize the action necessary to effect change. And the vector spaces represented by r dot and s dot are generated by the sum of all perturbances and quantum oscillations, which are mathematically represented by the weight function within the Sturm-Liouville equation. As a result, the derivative of the Hamiltonian is related to any changes in position and momentum and time, and therefore can be calculated by taking the partial derivatives of these eigenvectors. The phase-space distribution rho rs describes the probability of a particular system state being selected from the total phase space volume, given the dimensionality of R and the dimensionality of S. And this Levy equation yields the evolution of this volume, rho rs, over time t. And as a result of geometrical constraints, all of these state vectors are conserved across the system, and the vector field of r dot s dot has zero divergence. And that permits temperature and energy to be conserved across the system. So that gives us the full continuity equation with the entropy unchanged by the linear operation itself. But we know that things will change over the course of this computational cycle. The total amount of entropy produced will stay the same, but when correlations are found, we can redistribute that energy back into the system. And the mechanism for doing that is by solving for the Hamiltonian operator. So because the partial derivative of the density matrix equals 0, the continuity and the probability density can be made equal to 0. And because the vector spaces r dot and s dot are defined in relation to the Hamiltonian operator, the continuity laws persist while taking the second derivative of the Hamiltonian operator to identify the observable boundary of the total volume of possible system states, which of course is a set of eigenvalues for the system identified over this time evolution. And this equation relates the overall probability density for the system with the Hamiltonian operator, which describes the distribution of energy across the system. It also relates the position and momentum vectors directly to the Hamiltonian. And once a trace is taken across the density matrices for Rx and Sx, the weight function Wx can be resolved in relation to the other parameters. And that means we can solve the Sturm-Liouville equation and identify the optimal redistribution of energy states. And again, it's really worth thinking about what's happening here. Ultimately, there's no way to achieve spontaneous acceleration unless you combine all component pure states for every electron in the system, integrating all possible positions, momenta, and energy states. That gives us all possible accelerations, and then we can identify the one that best fits with a present environmental context. So once we have a system-wide complex valued probability density, we can take the second derivative of the Hamiltonian operator to identify the most optimal system state. And that'll yield each of the eigenvalues for the system. And that means we found the observable boundary for the complex valued probability density at the end of that time evolution, which is, of course, the observable system state. And we've done this by compressing entropy and reducing all of these probabilities to a single system-wide outcome with assigned values for every particle. So again, there's no way to achieve voluntary initiation of behavior without being able to spontaneously accelerate. And there's no way to spontaneously accelerate without completing a non-deterministic computation and redistributing energy into an optimal configuration across the system. So we've modeled how quantum information is generated, how we integrate all possible component states to get a density matrix describing all possible system states. And we've modeled this non-deterministic computational process as a unitary change in basis or as the time-dependent evolution of a Hamiltonian operator. So now we can resolve the system state and identify the mechanics underlying our thermodynamic computing cycle through the generation and compression of entropy. So system A was perturbed over time as we integrated the probability states and the Hamiltonian operator to create a volume of probability. So now we can take the derivative of that volume of probability and the Hamiltonian operator to define the surface boundary region, or how energy is distributed across the observable system. And this is called the Hellman-Feynman equation, and it resolves the Schrödinger wave function, allowing all component particle states to be transiently defined in accordance with the laws of electrostatics. So here we find the total energy E held by the system is related to any parameter lambda, which contributes to the Hamiltonian operator, like a shift in position, momentum, atomic orbital, electrical field strength, or magnetic moment. And as a result, the derivative of the value of E is related to the inner product of the state vector psi and the derivative of the Hamiltonian, both with respect to the parameter lambda. And this process reduces the complex valued probability density into a single actualized and observable state, with a single non-deterministic outcome for each eigenvector. And then things, of course, kick off again with renewed momentum. So once the two particle systems collide, physical constraints are introduced to the combined system, and a mutually compatible state has to be found. And this calculation, which solves the wave function equation, is equivalent to finding how the matrices commute through a unitary change in basis. And remember, the unitary change in basis is defined by the time shift operator, which is the imaginary unit over the reduced Planck constant multiplied by the time-dependent Hamiltonian. So any reversal to the direction of time causes positive energies to become negative, a result which is disallowed by the first law of thermodynamics, unless the spin is also reversed with the introduction of an electric dipole moment. An electric dipole moment is a spontaneous shift in the energy state of an electron in the presence of an external electric field, and this event occurs naturally upon probability density reduction as eigenvalues are calculated. And the Hellman-Feynman theorem tells us how this happens. It states that a dipole moment is induced by the resolution of the wave function in a manner proportional to the newly defined distance between atoms. Now we can find out how uncertainty is refreshed upon solving the wave function. First, we'll apply the Pauli exclusion principle so that all particles meet this Boolean satisfiability criteria. Every particle with some position at time t also has some momentum and energy state. But there's another criteria. The state of that particle cannot be identical to any other particle in the system because then those two particles would be identical and the universe will have lost mass. That outcome is prohibited by the first law of thermodynamics because energy can be neither created nor destroyed. So every particle has to find its own state and satisfy this Boolean logic. So every particle has some position along the x, y, z axes and some energy state, phi, at time t. And that set of values cannot be identical to any other set of values. Step 2. Now we can collapse the wave function or reduce the density of possible system states with the Hellman-Feynman equation. And when we solve for the Hamiltonian operator, we're solving for how energy is redistributed across the system. And obviously, this is all happening at the same time, but we're separating it into steps to clarify the various aspects of this computational process. Now, step 3. As the Hamiltonian is solved, we flip the spin. Since the expectation value of the energy state for a given particle is proportional to the expectation value for its spin, any negative energy shift causes a sign shift affecting the spin, and time symmetry is broken. Step 4. Now we'll observe van der Waals forces emerge. Since solving for position reduces uncertainty, momentum must become more uncertain in accordance with the Heisenberg uncertainty principle and the Hellman-Feynman theorem. Essentially, solving for position triggers a dipole moment, a shift in charge distribution across the atom, causing a boost to angular momentum for every atom whose uncertainty is abruptly reduced. And that dipole moment is 1 over r to the 7th, with r being the newly defined distance between an atom and its neighbors. These dipole moments are the product of a permitted violation of time reversal symmetry, with the computational process itself affecting causation within the system. And so, within our thermodynamic system, we can expect that van der Waals forces will emerge between sodium ions outside each neuron and atoms within the lipid bilayer of the neural membrane. And these forces are due to the dipole moments prompted by wave function collapse. Now, step 5. We'll observe new probabilities emerging as a function of time in accordance with the von Neumann projection postulate, with the density matrix being refreshed as a new computational cycle begins. That is, as new perturbations from the environment and quantum oscillations inherent to the system affect the emerging system state in the present moment. So the wave function is resolved and energy is redistributed by solving the Hellman-Feynman equation. But any negative energies cause a spin to flip, thereby breaking time reversal symmetry. The dipole moment is 1 over r to the 7th, with r being the radius between atoms upon resolution of the wave function. So now these atoms have a defined position and a new boost to their angular momentum. And the van der Waals forces induced between these ions and the nonpolar lipid membrane may cause some additional leak of ions into the neuron due to the induced drop in membrane resistance. And in neurons already in upstate, this ion leak may be sufficient to reach action potential threshold, open voltage-gated ion channels, and allow a flood of ions into the cell. Resolution of the wave function could therefore exert change on the neural network state. And this event is predicted to cause synchronous firing in sparsely distributed neurons across the network. So now we can summarize the cyclical process in terms of quantum mechanics. First, we generate a set of possible system states, with the state of each neuron in the network being a mixed sum of component pure states, and the intrinsic uncertainty or Heisenberg uncertainty of an electron will populate that probability density. So these states are integrated together to form a cohesive information set. The probability amplitudes for all possible scalar values of distance and time and energy state will be described by a time-dependent Schrödinger wave function. And the information held by the system is really the geometry of these combined interdependent wave functions. So then we'll take the derivative of this probability density and identify observables or eigenvalues on the boundary region. And we do that by applying the Hellman-Feynman theorem to calculate the Hamiltonian and redistribute energy across the system. And that process resolves the Schrödinger wave function, collapses the probability density. So we have a defined system state with a non-deterministic computational outcome. And the solutions are naturally constrained by the Pauli exclusion principle, which disallows particles from occupying the same state. So once the position, momentum, and energy state of every electron is defined, the state of every ion inside or outside a given neuron becomes defined. And neurons either reach action potential threshold or they don't. And remember, the likely outcomes are given by the thermodynamic constraints of the system at each synapse, which are defined by structural remodeling after past experiences. And once uncertainty is resolved and the computational cycle is completed and each neuron fires an action potential or not, uncertainty grows again as a function of time. As soon as the state of each particle is defined, uncertainty is refreshed by those induced dipole moments, and the system state evolves from there. So you may be asking, is the brain really a quantum computer? Certainly doubt has been cast on this hypothesis. And putting aside whether this doubt is just a reflexive reaction to the mysticism that often surrounds quantum mechanics, we can actually evaluate this question quite rigorously, because it's important to know if the brain is a classical deterministic system or a quantum computer. The answer to that question has a lot of implications for neuroscience, for philosophy, for computing, for physics. So the way we address this question was established by the physicist Max Tegmark, who published a paper in the year 2000 entitled "Why the Brain is Probably Not a Quantum Computer." So how did he come to this conclusion? Well, he calculated the decoherence timescales of sodium ions interacting with the neural membrane and found that quantum fluctuations are not likely to contribute to signaling outcomes. And this is certainly compatible with the behavior of spinal neurons and peripheral neurons, which are robust to quantum level noise. But it's really in contradiction to what we know about the behavior of cortical neurons, which exhibit spontaneous fluctuations in membrane potential. So we can take a closer look at these calculations and the assumptions behind them. Tegmark's calculations for the decoherence timescale of sodium ions at the neural membrane are the inverse of n, the number of ions needed to cross the neural membrane to reach action potential threshold, little n, the density of these ions, sigma, the scattering cross-section, and v, the temperature-dependent velocity of these ions. And Tegmark pointed out in this foundational paper that the superposition of an ion decays exponentially on a timescale that's proportional to the mean free time between collisions. And since the superposition of neuronal resting and firing states involves n superposed ions, the coherent state gets destroyed on a timescale that's proportional to the number of ions needed to affect a state change. And so he calculated the decoherence timescale for sodium ions at the neural membrane by substituting values for each of these variables. And he found the estimated decoherence timescale to be around 10 to the minus 20 seconds. Where the number of ions needed to cross the membrane, n, is 10 to the 6th, the density of ions is around 120 millimolar, and the velocity v of each ion at 37 degrees Celsius, or 310 degrees Kelvin, is estimated as the square root of kBt over m, or 10.6 meters per second. The Coulomb scattering rates were estimated to be really high, with little empirical data available at the time. But Coulomb scattering rates for mammalian cells have been modeled in much greater detail recently, with a new estimate for sodium ions at around 32.8 square nanometers. We can also include a better estimate for the number of ions needed to reach action potential threshold during a cortical upstate as 10 to the second rather than 10 to the 6th, and can recalculate the estimated decoherence timescales. And these new decoherence timescales are 0.4 milliseconds. The new Coulomb scattering rates, which are based on really detailed and relevant studies, yield a much longer decoherence timescale. And it's worth noting this decoherence rate of approximately 2,500 hertz is very similar to the exchange rate of sodium-potassium ion pumps embedded in the neuronal membrane. The rate of stochastic charge flux due to quantum oscillations is essentially balanced by this rate of sodium-potassium exchange. And so any burst of temporally coincident events within this time frame will contribute to changes in the neuronal state. But it's worth noting this calculation is only applicable in cortical neurons in upstate, since other neurons require a lot more simultaneous charge flux to gate a state change. So this mathematical model asserts that the resolution of quantum uncertainty can affect neuronal signaling outcomes. I am actually asserting that a non-deterministic computational process is responsible for consciousness and affects causation within the encoding structure. This is an extraordinary claim, so it's worth going through the process in detail. Causation can only be achieved by breaking time reversal symmetry. And in the thermodynamics model, we saw this happen with a relationship between Gibbs free energy and the Nernst equation, as the compression of entropy paired with a release of free energy contributed to fluctuations in the resistance of the neural membrane. That ultimately prompted charge flux and triggered the opening of voltage-gated ion channels. So now we can look at this same event by modeling the mechanics underlying that process. And as before, once two particle systems collide, physical constraints are introduced to the combined system and a mutually compatible state has to be found. A unitary change in basis drives this computation, and we went over the unitary change of basis and the redistribution of energy and changes to spin that occur when that calculation is completed, as a wave function or probability density collapses. But we can look at this in another way by modeling the contribution of quantum oscillations to thermal fluctuations at the neuronal membrane. If the time-dependent perturbation in ion behavior relies on any spontaneous changes to electron spin or energy state, then the ensemble average of each observable, which is a measure of fluctuation, will be related to the response function, a measure of dissipation, in the frequency domain. This relationship essentially models how the oscillatory behavior of quantum systems along a complex axis affects the thermal dynamics of the observable system. And here, theta is the Heaviside step function, and the response, chi of t, provides an expectation value for x of t, where x of t is a time-dependent observable subject to thermal fluctuation in a dynamical system. And so the time-dependent equation and its Fourier transform are given by these two equations. And if the eigenvalues are to be real, the sum of the real part and the imaginary part of the response function over some time evolution must also be real. The full response function is given by the sum of the real part and the imaginary part of the response function. So now we can look at these components more closely. The real part of the response function is given by the integration of all time-evolved events across the real axes. And the imaginary part of the response function is given by the integration of all time-evolved events across complex axes. So here, the energy of quantum fluctuations is related to the frequency and the hyperbolic cotangent of the probability density, where beta equals 1 over kBt. And the classical power spectrum is related to the complex valued quantum spectral density in such a way that quantum noise can contribute to thermal fluctuations under certain conditions. So what are these conditions? If E is greater than kBt, with a high temperature, a broad distribution of electrons across energy states, and low occupancy of energy states, then the quantum contribution to ion behavior is negligible, and the behavior of ions will reduce to classical Boltzmann-Maxwell statistics. If E is less than kBt, with electrons at low frequencies obeying the Rayleigh-Jeans law, then the quantum contribution to ion behavior is also negligible. And again, the behavior of ions will reduce to classical Boltzmann-Maxwell statistics. Only in cases of high particle density and high occupancy of energy states, when the energy held by an ion is greater than its chemical potential and E is greater than kBt, will quantum fluctuations actually contribute to ion behavior. And this is predicted to be the case in the mammalian central nervous system. If quantum fluctuations do contribute to ion behavior in biological systems, then E must be greater than kBt. And that corresponds to high energy particles within the infrared range of the electromagnetic spectrum. And so that's what we should expect to see if we look for quantum energy release upon completion of a thermodynamic computing cycle. And so in summary of this mechanics model, and this slide is going to look familiar, we have a far from equilibrium thermodynamic system that's capable of both generating information and extracting correlations in the system state. We have a network of 80 billion computational units that's capable of storing more information than would be possible for 80 billion transistors. We have an enormously energy-efficient system that produces a lot of information or possible system states, but then compresses that information to release free energy. And we have a system that allows the resolution of uncertainty to drive signaling outcomes across the network. And we have a system that uses the free energy released when uncertainty is reduced to achieve spontaneous acceleration. And this list is really surprisingly similar to the conclusions that we got from the thermodynamics model. We're just modeling the same process of computation with different mathematical models. So now we can go through a mathematical model of non-deterministic computation in terms of holography. This is a third model that goes through the same cyclical process of information generation and compression, but with another mathematical approach. Now, this is pretty astonishing, but a cohesive stream of perceptual experience corresponding to incoming data from the sensory apparatus just naturally emerges from this mathematical model. We have probabilistic coding, that is, neural membranes capturing probabilistic particle states and encoding that movement of charge over time into the voltage state of the neural membrane. And that probabilistic coding, that capture of complex waves or probability amplitudes, is paired with a representation of information content. There's no way to separate the two. If you have a polymer recording surface, any complex waves that are captured by an encoding structure will be holographically projected and reconstructed into a representation of the original wave function. So we can go through this process of probabilistic coding again and describe it in terms of wave mechanics, and in doing so, we can find out how an internal representation of reality is constructed by the brain due to the anatomical and physiological features of cortical neurons. It's worth mentioning, though, before we dig into the details, that the idea of describing consciousness in terms of holography is not new. Dennis Gabor and others suggested it during the 1960s, about 2 decades after holography was discovered. But the theory was never formalized in a way that was compatible with neuroscience, and the idea always had this whiff of mysticism about it. In the years since then, the holographic principle has come to be appreciated as a fundamental law for how information operates, and it's really less mystical and more just a process of linear transformations on probability amplitudes in high-dimensional vector spaces. But before this idea was really generalized, Gabor and his colleagues did make some interesting observations about the similarities between holography and conscious experience. First, they pointed out that perceptual experience doesn't seem to be reality itself, but rather a subjective reconstruction of it. And they also pointed out that memory is a kind of stored information which requires some kind of encoding structure. And most intriguingly, they found that the Fourier transform of noise in cortical neural networks actually corresponds to the periodicity of synchronous neural firing. And this is analogous to the Fourier transform that we just performed with the Kubo fluctuation dissipation theorem when we modeled how quantum oscillations contribute to cortical neuron signaling outcomes. And that only occurs when temporally coincident events converge on a neuron within the very short time frame of membrane potential rectification kinetics. And again, this was discovered in the 1960s. But again, these researchers didn't really formalize the idea of the brain as a holographic recording surface and figure out how a reconstruction of reality could be created by the biophysical, anatomical, and physiological characteristics of cortical neurons. So let's do that. Let's formalize this idea. First, let's go over the assumptions. The assumptions are really just that we'll be dealing with complex waves impinging on a polymer membrane surface. In a classical hologram, we have an object beam interfering with a reference beam with some phase angle difference onto a polymer recording surface. And that allows an image encoded on the recording surface by the interference of complex waves to be reconstructed into a hologram. And what I'll be arguing is that we're dealing with the same thing here, but instead of photons arranged across 3 dimensions, encoded on a 2-dimensional holographic recording surface and reconstructed into a 3-dimensional hologram, we have complex waves or probability amplitudes that are distributed across 5 orthogonal axes. And they're impinging on a polymer membrane surface that's defined across 3 spatial axes and time. So events in reality can be reconstructed representationally, and the information content that's encoded on the neural network structure will form a cohesive stream of perceptual experience. So we know we have complex waves, and we'll model these in a moment. But first, let's just check whether the neuronal membrane meets the requirements for a holographic recording surface. These criteria include a charge detecting surface comprised of organic or synthetic polymers with a linear relationship between energy exposure and the amplitude of the reconstructed wave, which attains signal fidelity. We need a flat spatial frequency response to ensure signal capture, a large dynamic range, providing a good signal-to-noise ratio, a high-quality and lossless material, affording efficiency in projecting the hologram, and a sensitivity to low energy exposure to achieve fine signal detection, as well as protection from environmental factors that could impact functionality. The lipid membrane of the neuron meets all of these characteristics. It's a polymer sheet with dense dendritic arbors for signal capture, a large dynamic range, and a high sensitivity to temporally coincident signals, which provides signal extraction. It's also generally capable of fine signal detection, and it's certainly protected from the environment. And of course, the membrane of every cell in the body is composed of phospholipids, but only cortical neurons are sensitive to probabilistic particle behavior in gating signaling outcomes. So we can focus on those cells in particular. So first, we can look at the composition of the cellular membrane. And we can compare the lipid tail saturation of the plasma membrane of the average mammalian cell with a lipid tail saturation of the average mammalian brain cell. This group completed a really detailed analysis of the lipid composition of the plasma membrane, and we can see there are a lot more unsaturated fatty acids in the plasma membrane of neurons compared with other tissues, both in the outer leaflet and in the inner leaflet. These unsaturated fatty acids affect the rigidity of the membrane, and they also affect the permeability of the membrane to ion leakage. And we can also see there are lower amounts of cholesterol in the outer leaflet of neurons compared with other types of cells, and higher amounts of cholesterol in the inner leaflet. And these cholesterol molecules will affect the packing of lipids within the cellular membrane. So again, they'll affect rigidity and permeability. And that'll affect the dynamics of the cellular membrane. So what we have here are temporal dynamics in neural cell types. Because of an increase in unsaturated fatty acids throughout the neural membrane and a decrease of cholesterol molecules in the inner leaflet, there's a lot less rigidity in neural cell types compared with most other cells of the body. So again, the plasma membrane of every cell in the body is composed of phospholipids, but cortical neural membranes have two key unique properties. They're sensitive to probabilistic particle behavior in gating signaling outcomes. And now we see they're also defined across 4 axes instead of just 3. They're defined across the X, Y, and Z spatial axes, and they're also defined across time as well. And that's going to allow these polymer membrane sheets to capture our complex waves. It's worth also mentioning that lipid composition affects the area-independent dipole potential for atoms within that polymer sheet. In black, we have phosphocholenes, and in white, we have phosphoethanolamines, with different esterification profiles. And I won't get into the details here, but suffice to say that different fatty acids contribute to different phospholipid membrane compositions. And these different phospholipid membrane compositions will lead to different membrane permeability. So these dynamics are directly linked to the opening of ion channels embedded in these polymer structures. So we'll be modeling complex waves impinging on polymer surfaces. But rather than 3-dimensional complex waves impinging on 2-dimensional surfaces, we'll be modeling 5-dimensional complex waves impinging on 4-dimensional surfaces. And that means we'll encode and project information in accordance with the holographic principle. So we'll start with a classical hologram, and we'll just go over the mathematics describing how a classical hologram works. Here, we're measuring the phase angle between ER and EO, given by this equation. And we're integrating N, the density of electrons with charge E, over a path of length L during time t, where lambda is the wavelength of the electron, m is the mass of the electron, c is the speed of light, and epsilon is the permittivity of free space. And now we'll generate fields from these complex waves. The electrical fields generated by ER and EO are given by these two equations, with a phase angle difference between them. Where ER and EO are the electrical fields of the reference and object beams, respectively. J is the imaginary part of the complex wave. Omega is a constant defined by 2 pi over lambda. And phi is that effective phase angle between the object and reference waves after elapsed time t. And so we're going to pay attention to the dimensionality here. The spherical waves generated by ER and EO are given by UR and UO with a phase angle difference between them, where rho is the position of point E and R provides the coordinates of the recording plane. The hat denotes a unit vector across the identified coordinate plane. And these variables chi, eta, and zeta are coordinate values in 3 spatial dimensions. So now we'll find the geometry of this relationship between the point source of the complex wave and the recording surface. The distance between the point source and the coordinates of the recording plane is given by the square root of the sum of squares. And since z equals 0 for a flat recording surface, this equation simplifies, and we only have those 2 dimensions to worry about. So now we can look at the process of interference between the object beam and the reference beam. The intensity of the combined beams is given by the square of the sum of those spherical waves. And here the x indicates the complex conjugate. UR is the spherical wave generated by the reference beam, and UO is the spherical wave generated by the object beam. And the transmittance of the combined beams is given by the integration of all of these intensities, where alpha is a constant accounting for a uniform background electrical field, beta is a constant measuring the sensitivity of the surface to an electrical pulse of wavelength lambda, and tau is the duration of exposure of the surface to the electrical pulse of wavelength lambda. And now we can reconstruct the image provided by the sum of all these point sources, which are interfering waves impinging on a polymer recording surface. The electrical field reconstructed by the combined beams is given by the transmittance, multiplied by the spherical wave generated by the reference beam, where T is the transmittance across the 2-dimensional recording plate, and UR is that original reference beam. With algebraic substitution, the equation expands. And here, the first and fourth term represent the 0th order diffraction, essentially the original reference wave. The second term represents the true image. And the third term represents the phase conjugate or virtual image. And it's really the spatial separation between these 2 terms that generates the hologram. So we'll find that the interaction of the reference beam and the 2-dimensional holographic recording surface that's encoded that information is able to reconstruct a 3-dimensional image. So we've gone over a 3-dimensional holographic projection formed by photons striking a 2-dimensional surface. But these mathematical laws can be extrapolated into any system that encodes complex waves as information on a polymer recording surface. The dimensionality of the holographic reconstruction just increases with the dimensionality of the waves and the encoding structure. So each electron is represented by a wave function, which models its possible and likely positions and energy states. And that generates both a reference path and any number of object paths. So each electron is modeled as an object with probability amplitudes distributed across the x, y, z, and energy axes. And so the probabilistic state of each electron is best described as a density of possible trajectories relative to the reference beam, which involves no change or no phase angle difference from the previous state. And the distance and energy state of each electron is calculated in relation to each polymer membrane surface, and that affects the voltage of each polymer membrane surface in the vicinity. And so these voltage states are also probabilistic in the present moment. But let's keep the focus on the 4-dimensional state of each electron impinging on each of these 3-dimensional membrane surfaces. So now we can map out this complex wave, or distribution of probability amplitudes, which is defined across 4 orthogonal axes. And we'll map out all of these point sources as they impinge on a 3-dimensional surface, that is, every region of neural membrane in the vicinity. The distance between each point source and the coordinates of the recording plane is given by this familiar equation. But now, since z does not equal 0 for a neuronal membrane surface, the equation does not simplify. Here, rho is the position of point E across 4 dimensions. R provides the coordinates of the recording plane across 3 dimensions. And chi, eta, and zeta are coordinate values across those 3 spatial dimensions. And now we can reconstruct the information that's provided by the sum of all these point sources, caused by the interference of complex waves impinging on the polymer membrane surface. The electrical field constructed by the combined beams is again given by the transmittance, multiplied by the reference wave function, which is again no change in energy distribution from the previous state. So we're subtracting the sum of all intensities from the background electrical field while adjusting for the exposure time and the sensitivity of the recording surface. And here, UR is the reference beam, and UO is the object beam with some phase angle difference to the reference beam. And that phase angle difference is the difference in that distribution of probability amplitudes. And of course, here the coordinates of the point source distribution across the recording plane are defined across 3 dimensions, not 2. So each electron is represented by a wave function which models its possible and likely positions and energy states, generating both a reference path and any number of object paths. And the integration of probabilistic particle behavior in a 3-dimensional neural network generates a combined wave function, describing all possible states for the entire system. That probability density is the mathematical equivalent of information, and the encoded information is just naturally projected into a higher dimensional volume in accordance with the holographic principle. But each electron also has some trajectory across time. So each electron is really best modeled as an object with a probabilistic position defined across x, y, and z spatial axes, and a probabilistic orbital energy state after some amount of time has passed. And all 5 of these values are intrinsically uncertain. They're scalar multiples of Planck units mapped along 5 orthogonal axes, x, y, z, energy, and time. And so the probabilistic state of each electron is essentially a density of possible trajectories across 5 orthogonal axes relative to each neuronal membrane, which is also, remember, not only defined across 3 spatial axes, but also changing over time, as those unsaturated fatty acids cause the membrane surface to ripple on a millisecond or sub-millisecond timescale. Now we can find out what happens with these distributions of probability amplitudes when the complex waves are defined across 5 orthogonal axes and impinging on a 4-dimensional surface. Again, the distance between each point source and the coordinates of the recording plane is given by this equation. But again, the equation does not simplify. We have to describe the membrane surface not only with 3 spatial dimensions, but also with a time dimension. So here, rho is the position of point E across 5 dimensions. And R provides the coordinates of the recording plane across 4 dimensions. And chi, eta, zeta, and theta are coordinate values across that dynamical structure. And now again, we can reconstruct the information that's provided by the sum of all these point sources, which are changing over time. And again, we're modeling the interference of complex waves impinging on the polymer neural membrane surface. But now we're comparing the probabilistic trajectories of each point source over 3 spatial dimensions and the time dimension. So we're getting interference between complex waves, and that'll be encoded across 4 dimensions. And that's going to allow us to determine the optimal energy distribution across the system. Since eigenvalues are assigned at the completion of every computational cycle, every actualized system state that's occurred in the past has some assigned location and time. And so what we're doing here is integrating these individual system states to create a temporal sequence of neural network states. And that sequence of neural network states will be paired with sequences of information content. So what we want to find is the most likely system state in the present moment, given the historical trajectory of each particle in the recent past. Okay, so the electrical field reconstructed by the combined beams is once again given by the transmittance multiplied by the reference wave function, where UR is the reference beam, and that's the previous system state with some energy distribution and some assignment of positions over some time distribution. And UO is the every single possible object beam, and every single object beam will have some phase angle difference to the reference beam. And that phase angle difference is again the difference in the distribution of probability amplitudes that are distributed across 5 orthogonal axes. And so now the coordinates of the point source distribution across the recording plane are defined across 4 dimensions. In a temporally persistent, non-dissipative thermodynamic system, individual system states can be integrated into temporal sequences. And the integration of wave functions, each of them representing the neural network state at a single moment in time, should generate a cause-effect model of the world. Temporal sequences of perceived events are encoded by temporal sequences of neural network states. And that resulting world model should be unique. It should be only accessible by the neural network that produced it, and it should be centered on the body, which collects data through the sensory apparatus. And so this mathematical model predicts that perceptual awareness is a holographic projection, representing the data collected by the sensory apparatus and encoded within the neural network structure. And the accumulation of these holographic projections over time forms a world model built on sequential experiences. And now we can take a closer look at the interference between wave functions. Our probability densities describe how energy states can be redistributed across the 3 dimensions of space over time in a non-dissipative thermodynamic system. And the interference between complex waves is expected to amplify high likelihood neural network states while canceling out noisy states that are not compatible with reference wave function. And so a new wave function interacting with a reference wave function should lead to a new confidence in the most probable present state for the entire system. And that can be understood as a contextually relevant mental model informing the most probable present state for the system by acting as a reference wave in relevant computations. And of course, because of the holographic projection, we're able to experience all of this happening. And we remember our phase angle difference in system states, where n is the density of electrons. Taking the derivative of this equation yields a single observable state for this electron density. Remember, the integrated neural network state in the present moment is represented by a hyperspherical wave or wave function. The reference wave UR is identical to the immediately previous neural network state. The object wave UO has experienced some change. And again, there are many possible object waves. The interference pattern between the reference beam and all possible object beams can be considered a function of the phase angle difference between the previous neural network states and the current neural network state. So what we're describing is an information compression event with a constructive and destructive interference between complex valued probability amplitudes, yielding a non-deterministic computational outcome or an observable system state. In other words, taking the derivative of that electron density, or that volume of information content, is equivalent to calculating the Hellman-Feynman equation. And again, we're solving for the redistribution of energy across the system by solving for the Hamiltonian operator. So we find that dividing the total volume of electron density by the derivative of the phase angle phi is equivalent to dividing the derivative of the total energy of the system by the derivative of any factors contributing to the probability distribution. So again, we're finding the path taken through the probability distribution to arrive at some observable system state. And so any change from a previous or reference neural network state has to include some reduction of the wave function in order to reduce the number of possible neural network states. The system undergoes a non-deterministic computing process, and in doing so, it reduces the expanse of possible system states into the most likely and consistent state. And then every electron is assigned some position and energy state before embarking on a new trajectory. And in practical terms, the system state is, of course, restricted to compatible and permitted states for all particles within the system, since they can't occupy the same position, spin, and energy state. And so the value of the derivative of the phase angle has to provide a compatible and permitted state for all particles in the system. And while this calculation is going on, the system produces a qualitative holographic reconstruction of the information it's encoded. These wave functions not only generate a stream of perceptual information content, but they also constructively and destructively interfere with the reference wave function to distinguish the most likely and consistent state for every particle in the system. And so that representation of information content is always paired with a non-deterministic computation. I like this model a lot. It's great to think in terms of thermodynamics, with a neural network interacting with its environment and finding a compatible state with its environment. I think that's a really intuitive approach. And if we track the thermodynamics, the distribution of energy, we find that compatible state is achieved through the cyclical generation and compression of entropy, as predictive value or meaning is extracted from that information. And it's also great to think in terms of quantum mechanics, with every electron in the system having some probabilistic state and the whole system pulling together to find the most optimal configuration as a whole. And that connects back to the compression of information and the release of free energy, with a redistribution of the Hamiltonian occurring as that non-deterministic computation is completed. But I really like this holographic model because the mathematics connect with something that we've all seen in real life. We just have to extrapolate to a few extra dimensions, and we get this stream of perceptual experience unfolding over time. And what's even more exciting is that the math directly connects back to the mechanics model with the derivative of that integrated wave function matching the Hellman-Feynman equation and giving us a non-deterministic computational outcome as those complex waves constructively and destructively interfere on the polymer neural membrane. And so now it'll start to make sense why I'm calling this thing Conifold Theory. A conifold is a known structure in physics. It's a five-dimensional shape formed by linear algebraic transformations that obeys the holographic principle. And I'm proposing that it can emerge from any heat-trapping thermodynamic system that engages in quantum information processing. A conifold has a three-dimensional point in the observable universe, which acts as an encoding structure. And it has an information streaming dimension with all possible system states in the present moment superpositioned across 4 dimensions. And it has an information accumulating dimension with all historical system states summing geometrically to form a 5-dimensional base. And that's what I'm arguing consciousness is. It's a process of computing information. We encode information in our brains, we stream information content to achieve perception, and we accumulate information content to form cognitive models. And I'm arguing that this is a physical process, a process of probabilistic computation that takes place in cortical neural networks. So if we want to imagine this shape, we can take a regular cone and imagine that point is not 0 dimensions, but actually a full 3-dimensional structure. And all possible energy states in the present moment extend into a 4th dimension, like the lines radiating out from this point. And the accumulation of all of these system states integrated over time forms the 5-dimensional base of the structure. So this geometrical structure that's defined across 5 orthogonal axes and formed by linear operations is called a conifold. And I think that's what we have here. So that's why I'm calling this theory Conifold Theory. And so in summary of the holographic model, the probabilistic encoding of information by a cortical neural network in the form of complex waves naturally produces representative information content. And so this model demonstrates that streaming perceptual experience is a natural byproduct of neural computation. And that has a number of philosophical and biophysical implications. First of all, this model suggests there is a reality out there, and consciousness is a process of perceiving it. Secondly, perceptual experience is exclusively accessed by the encoding structure. Thirdly, perceptual experience is representative of incoming sensory data and continually updated as new sensory data arrives. And interestingly, variance in the lipid composition of the neural membrane between individuals, as well as individual variance in the sensory apparatus, could contribute to variance in the quality of perceptual experience, because it defines this fine signal capture contributing to that holographic reconstruction. And finally, perceptual experience may play a role in devising cognitive models and triggering subsequent behavior because the subjective awareness of information content is coordinated with a process of non-deterministic computation. So this theoretical framework starts with two simple assumptions: that cortical neurons undergo probabilistic coding, and that cortical neurons detect stochastic charge flux by encoding interfering complex waves on the polymer membrane. And these two simple features, which we know from neuroanatomy and neurophysiology, prompt the system to not only undergo non-deterministic computation, but also represent the data being encoded. So now we can go over the entire theoretical framework, including a summary of the theory and the minimal assumptions of the theory, the neuroscientific predictions generated by the theory, and the explanatory power of the theory. So in summary of Conifold Theory, we can say that identifying cortical neuron signaling outcomes requires modeling these cells at action potential thresholds when they're suspended between on-state and off-state, with stochastic charge flux contributing to a dynamic membrane potential. The outcomes of cortical neurons are not deterministic, they're probabilistic. And so we have to use the mathematics of probabilities to model how the system works. And all three mathematical models of non-deterministic computation that are given in terms of thermodynamics, quantum mechanics, and wave mechanics reveal that energy is being cyclically expended and recovered as information is generated and compressed. And all three mathematical models demonstrate how energy is periodically redistributed to physically process information and drive thermodynamic work within the system. And interestingly, we don't have to start with the assumption that consciousness exists. In this theoretical framework, it's just something that pops out as an emergent property of biological neural networks. A cohesive stream of perceptual experience corresponding to incoming sensory data, predictive cognitive models of the world and the self, and the voluntary selection of behavior just naturally emerge from this organic, non-deterministic computational process. This theoretical framework is useful. It is a theoretical framework for consciousness that does not stand in opposition to modern neuroscience, but rather enhances its explanatory power. Consciousness here is about information processing, how information is captured, encoded, and represented by cortical neural networks. Here, a thermodynamic computing cycle extracts a signal from the noise as information is physically processed. And this computation corresponds to the extraction of meaning from a messy dataset as information content is mentally processed. And so the features of consciousness, including perceptual experience, predictive processing, spontaneous self-remodeling of the neural network structure to store memory, non-deterministic signaling outcomes, and exploratory behavior all naturally arise from probabilistic coding in cortical neural networks. And so this theoretical framework is able to explain some of the more intangible features of consciousness in terms of cortical information processing. So we're not just looking at sensory input and motor output, we're also looking at how the cortical neurons actually generate perceptual experience, mental models of reality, and behavioral choice. And what we find is that a cohesive stream of perceptual experience is well explained by information capture and holographic projection through probabilistic coding by cortical neurons. And cognitive models, which accumulate over time during development and learning, are well described by thermodynamic computing. Here, predictive value is a thermodynamic quantity, which is extracted during computation. And the free energy released during information compression can then be used to do work, storing memory through remodeling of the neural network structure. And since information compression and the free energy release that accompanies it are equivalent to the amount of predictive value extracted, that is what is encoded into the neural network during synaptic remodeling. And so we tend to only remember things with predictive value that might be useful later. In this model, information processing does participate in causation, affecting signaling outcomes in cortical neurons. We may not be perfectly free, but we can engage in behavioral choice through non-deterministic computation. Now we can go over the assumptions of the theoretical framework. There are really only 3 assumptions in the theory, and they all agree with current evidence in neuroscience. The first assumption is that cortical neurons engage in probabilistic coding, allowing stochastic charge flux to affect the membrane potential. And for this reason, cortical neurons are better modeled as quantum computing units than classical computing units. Secondly, the membrane of a cortical neuron is a polymer surface that meets the dimensionality and material requirements to act as a holographic recording surface, with a high sensitivity to charge flux and a large dynamic range. And so cortical neurons can both capture complex waves and project that information content in accordance with the holographic principle. And finally, we assume that cortical neurons have to expend energy to accomplish work. So we're following the laws of thermodynamics. And these 3 simple assumptions, which are well supported by empirical findings in neuroscience, allow us to perceive the world, build an understanding of the world, and choose our actions in the world. And so now we can go over the specific predictions generated by the theoretical framework. There's actually dozens of predictions, but we'll just go over a few of them. First of all, maintaining temperature and ion channel function are critical to healthy cognition. So high temperatures should increase the amount of energy available to create information. And so high temperatures should increase the probability density created by the cortical neural network and should therefore increase perceptual richness and potentially perceptual error. And conversely, an inability to maintain brain temperature should lead to a reduced probability density, corresponding to diminished perception and less energy available for initiating willed action. And that really has implications for age-related dementia in cases where metabolic efficiency declines with age. An excess neural excitation, for example, in the case of epilepsy, should lead to a reduced probability density. And that should correspond with diminished perceptual content, less information being available to parse, and so reduced memory formation during these events, and less energy being recovered by the system to prompt signaling outcomes. So you just have this rigid deterministic behavior. And excess neural inhibition should also lead to reduced probability density due to more deterministic outcomes in cortical neurons. And so with drugs like barbiturates, benzodiazepines, alcohol, or sedatives, you'd expect diminished perceptual content, less information being available to parse. And so again, reduced memory formation during these events and less energy being available to the system to prompt signaling outcomes and direct bodily action. So you have less activity in motor cortex, less motor control. And conversely, any drugs that increase the number of possible system states should expand perception and cognition. So you might expect the mechanism of action of hallucinogens to be increasing the number of excitatory postsynaptic potentials that are needed to achieve an action potential threshold. Next, there are predictions relating to the thermodynamics and mechanics of information processing. So we expect that information compression is paired with spontaneous release of free energy. And due to the conservation of energy law, the first law of thermodynamics, information compression must be paired with a release of free energy with E greater than kBt. And given the tightly controlled temperature of the mammalian central nervous system, that gives us a quantal energy release of photons in the infrared range of the electromagnetic spectrum. And this photon release is predicted to occur during perceptual tasks in a manner corresponding to event-related potentials, as synchronous activity in sparsely distributed neurons across the network correspond to multisensory perception. But this spontaneous photon release is predicted not to occur during ictal activity in cases of epilepsy when cortical neuron signaling outcomes are deterministic rather than probabilistic. There are also some predictions relating to the generalizability of thermodynamic computation and the implications for consciousness in animals and machines. So first of all, any animal that exhibits non-deterministic behavior should also exhibit cortical or pallial upstates, spontaneous free energy release upon information compression, synchronous firing in sparsely distributed neurons, and remodeling of the neural network structure into a more ordered state. And conversely, any biological or engineered system that meets the anatomical and physiological requirements for consciousness given by this theory should exhibit spontaneous acceleration and spontaneous remodeling of the neural network structure, as well as searching independently for energy resources and going to sleep periodically in order to parse information overload. And these engineered systems should be able to exit a local minimum in the solution space and explore the environment with free behavior, which is something that's really different from current machine learning algorithms or artificial neural networks that are instantiated in classical computing architecture. This is a fundamentally different kind of computation here, and it generates spontaneous exploratory behavior. And if the structural and physiological criteria are met, you will end up with an engineered system that can perceive the world as it's solving problems and developing fine motor skills. So there are a lot of exciting and thought-provoking applications here and a lot to consider philosophically before we embark on that engineering. So now we can talk about the explanatory power of the theoretical framework. The theory explains how cortical neural networks naturally generate subjective perceptual experience. And that subjective perceptual experience is exclusive to the neural network that encodes it. It's tied to neural activity, but not strictly reducible to it. And it's representative of incoming data from all sensory modalities. In addition, the subjective perceptual experience is altered by changes to brain temperature and the presence of any drugs that affect the probable on-off state of cortical neurons. And here, observation is a bioenergetic process. So attention is the amount of free energy that's dedicated toward information generation when considering a stimulus. And salience is the amount of free energy recovered upon information compression when processing that stimulus. And so we can really think about conscious perceptual experience as how we're dedicating energetic resources toward gathering information about our local environment. And this theoretical framework accommodates predictive processing. Here, a single thermodynamic computing cycle yields an observation, that is, perceptual content or a predicted semantic truth statement about the local environment. And a temporal sequence of these thermodynamic computing cycles yields a predictive syntactical statement of causal relationships between events in the environment. So we're stringing together sequences of percepts to predict the likely cause and effect interactions, for example, between our own actions and subsequent events. And these sequences of percepts are, of course, paired with sequences of neural network states. And the redistribution of energy that happens upon completion of a thermodynamic cycle adjusts the set of possible system states, physically achieving Bayesian inference. And so the way that we move from a prior probability density to a posterior probability density is by a redistribution of the Hamiltonian. And we can also accommodate memory within this theoretical framework. Sequences of events with high predictive value will lead to information compression and the release of free energy, which is then used to do work remodeling the system structure. And cues with predictive value favor the recurrence of relevant sequences of neural activity. These are thermodynamically favored pathways. And so what we end up with is the emergence of exploitation dynamics in behavior. Exploration is favored, even though it requires energy expenditure, because it increases the amount of information available for parsing. And remodeling the system state is also favored, even though it requires energy expenditure, because it stores memory for later use. And so a rival energetic cost function guides behavior, with exploitation favored if sufficient knowledge is available to handle the situation, and exploration favored if knowledge is insufficient. And so all decisions are based on the minimization of energy dissipation, and will readily explore our environment, even if good enough solutions are available, because that process has its own reward of gaining predictive value. And so in this theoretical framework, we actually affect causation. Consciousness is not some useless epiphenomenon. It allows an organism to perceive reality, to parse predictive value, to build cognitive models, and to use all that information gleaned to choose the best actions in that context, the actions that are most likely to reduce the chances of energy dissipation. And so this theory asserts that the actual existence of a thermodynamically constrained free will. We can choose what to believe and what to do. But our actions are constrained by how much we have exercised our brains in the past, how much we're willing to entertain new possibilities, how much work we're willing to do to put into exploring our world and trying out new solutions. And so in this model, non-deterministic computation actually affects causation within the system. Quantum oscillations contribute to thermal fluctuations affecting the resistance of the neural membrane, the rate of ion flux, and the likelihood of reaching action potential threshold. And so cells in upstate that are already nearing action potential threshold, that contribution could be sufficient to open voltage-gated ion channels and cause the cell to signal to neurons downstream, thereby affecting a causal cascade. But it's worth noting that our actions are subject to both internal and external thermodynamic constraints. We may not be able to accept an idea. It may not be compatible with our pre-existing cognitive models. And we would really have to work to accommodate that new idea. We'd have to put thermodynamic work into that process of updating our cognitive model. And if the new idea contradicts our existing cognitive models, we're really unlikely to destroy those cognitive models to accept that new information. That would mean dissipating all of the thermodynamic work we put into building those cognitive models in the first place. But also, we might be able to consider an idea or imagine a solution to some problem, but then we're not able to execute the action. Or we execute the action, but it doesn't have the intended effect in the world. It doesn't actually cause the consequences that we intended, maybe because others were trying to get their way, achieve their goals in the world. And so those are external constraints that limit our abilities to affect causation or use our free will effectively. But overall, this theoretical framework says that consciousness is a natural, useful computing process. It allows us to perceive the world, understand the world, and navigate the world effectively. It is a tool for information processing. It allows us to continually explore the world and use that knowledge wisely. And that is really what we exist to do. And I'll leave it at that. Thank you for listening. I'm extraordinarily grateful to the Western Institute for Advanced Study for supporting this work, and I'm extraordinarily grateful for the opportunity to address this problem. I think that science is a formalized form of consciousness. It allows us to perceive the world, build an understanding of the structure and operation of the world, and then navigate the world more effectively with that knowledge. And so I'm really grateful to be a scientist and to engage in science and to present this work to you. So again, thank you for listening.